Welcome back to the Deep Dive. Today we're getting into a research paper that really fundamentally changes how we think about AI interaction. So forget about AIs trained to these perfect, clean sandboxes like Go or specific StarCraft maps. We're talking about an AI that doesn't just play a complex commercial video game. It kind of lives in it. It interacts with these huge open worlds just by looking at the screen and, well, pretending it has a keyboard and a mouse. It's really the ultimate test of generalization. Moving from that closed world mastery to something that feels a lot more like, well, messy digital humanity.
And this agent is called Lumine. It's a 7 billion parameter vision language action model, a VLA model. And you hit the nail on the head there. The real difference is the domain. Past AI breakthroughs, they were in these closed systems, right? Where the rules are clear, the goals are simple. But modern open world games are the total opposite. They are messy. You've got ambiguous goals. You have to navigate in 3D. The UI is always changing, and some tasks take, hours to complete. Lumine is a breakthrough because it's basically a working recipe for a generalist agent that can handle all that ambiguity, all that diversity, and do it in real time.
Okay, that just sounds like science fiction. So if the open world is the goal, what are the specific hurdles that a normal agent just can't clear? What are these 6 core challenges that Lumine was specifically designed to overcome?
Right. So the researchers basically laid out 6 big ones. First, you need scalable environments, which these games obviously are. Then multimodal perception, so combining the 3D world, the 2D menus, and text. Then there's high-level planning for those hour-long goals. Low-level control for the actual, split-second keyboard and mouse stuff, efficient memory over long periods, and then the final piece, real-time inference, so it can actually think and act fast enough.
Let's start with that friction point.
Yeah.
Low-level control. It seems incredibly hard for an LLM to decide on some big, abstract plan, but then to translate that plan into hundreds of precise little keyboard and mouse actions during a fight. That seems almost impossible if it's just looking at screenshots.
It is, and that's where the architecture of this VLA model really shines. So first, perception. Lumine looks at a 720p screenshot, but it only gets a new frame every 200 milliseconds. It's about 5 hertz. But, and this is crucial, it uses what they call a multi-turn dialogue format for context. So it's not just seeing the current frame. It remembers its last few actions and its own thoughts, its own reasoning. It builds up this 4-second history of what it's been doing.
So it's building a little narrative, like, okay, I just moved forward, I saw that chest, now I'm facing the wall. That's way better than just a single snapshot.
Exactly. And when it goes to act, the output is super efficient. It doesn't generate lines of code. It just generates a short, simple string that describes the action. So, key presses, and most importantly, relative mouse movements. That's your delta X and delta Y for looking around in 3D.
But that 200 millisecond gap still feels like a huge problem.
Yeah.
In a game, you click, you want an instant response.
Yeah.
If the agent is thinking for 200 milliseconds between every single action, the game would just feel sluggish, unplayable.
Yeah.
How did they solve that latency?
This is, I think, the most clever part. They call it action chunking. So the model only spits out a command string every 200 milliseconds, yes. But inside that one string is the prediction for 6 consecutive actions, 6 little chunks. And by predicting 6 moves at once, they get this continuous interaction frequency of 30 hertz, because each of those little chunks only lasts about 33 milliseconds.
Oh, wow. So that's how it feels human. That's how you get complex moves. You can't just tell it to jump. You have to, hold the space bar down for a bit.
Yeah.
The chunks let it do that.
Precisely. It allows for that sustained input you need in an action game, holding W and Shift to sprint, or chaining 3 different skills together without a pause. And they pair this with something called hybrid thinking. The model only does that deep, expensive reasoning, its inner monologue, when something changes, like a new enemy appears or it gets a new quest objective. Otherwise, it just predicts the action chunks directly. It balances that deep strategy with, pure reflex.
Okay, so action chunking and hybrid thinking solve the control problem. But let's be honest, we're still talking about a 7 billion parameter model.
Yeah.
Trying to make a decision in under 200 milliseconds. That's a massive computational lift. How on earth did they get a 25-fold speed up without, needing a supercomputer the size of a small country?
It took some really meticulous optimization on both the software and hardware side to hit that time limit. They squeezed every single millisecond they could out of the process, and that's how they got to that 25.3x speed up versus a standard setup.
What did that actually look like? I see terms like streaming LLM, tensor parallelism. That sounds like some pretty serious hardware jargon.
Yeah, let's break it down. First, streaming LLM. This is all about managing that dialogue history efficiently. Think of it like a really smart browser cache for the AI's short-term memory. It means the agent doesn't have to reread and reprocess everything it just did every single time it acts. It saves a huge amount of processing power.
Okay, so caching its own memory. That makes sense. It speeds things up.
Then you have tensor parallelism. Because the model is so big, a 7B model, they basically split its brain across 4 powerful GPUs. This lets them process different parts of the decision at the same time. It's just parallel processing for a giant AI. And then the last bit is speculative decoding, which is a clever trick to speed up the output. The system essentially guesses the next part of the action string before the full model confirms it. That anticipation shaves off critical milliseconds.
That level of optimization is, well, it's incredible. And the result is that the time it takes to act without reasoning is just 110 milliseconds.
Yeah.
That is shockingly fast for a system this complex.
It is. It's well within the real-time needs of a modern action game.
So the recipe works in theory, and it's fast. Now, for the real test, they benchmarked Lumine on Genshin Impact. And for anyone who doesn't know, that's a massive open-world action RPG. You need navigation, fast combat, puzzle-solving, menu management for hours.
Right, and the researchers didn't just test it on one small thing. They had it play the entire first main storyline, the prologue, Act 1. It's a sequence of 5 pretty demanding quests.
So, how did our digital prodigy do against us mere mortals?
Lumine Thinking completed the entire mission in 56 minutes. Now, to put that in perspective, a totally fresh human player took, on average, 78 minutes. An expert human player, 53 minutes.
Wow.
So it's right there with an expert. For an AI to autonomously play for nearly an hour with that level of human efficiency it's just a massive achievement.
I think the most important result here for me is the proof that the thinking part, that memory and reasoning is actually doing something useful. The success rate for the full Lumine thinking model was, what, 93.4%?
Exactly. And now you compare that to the version that only had the instructions, no thinking. Its success rate was just 66.8%. That history, that reasoning, it is absolutely vital, especially for things like navigating a complex menu or just walking around without it. The agent is always reacting to 200 millisecond old information, which means it might overshoot a button in a menu or, get stuck in a loop. The history lets it correct for its own built-in lag.
But, okay, if the whole model is a vision language action model, and its most common error was perceptual misrepresentation, so misinterpreting things like health bars, doesn't that mean the vision part is actually the weakest link here?
That is a really sharp observation. The errors weren't usually in execution. It knew what buttons to press. The errors were cognitive. It thought it saw something that wasn't there, or it misread its health because of some flashy visual effect. It really does suggest a vulnerability in how the model processes complex visual information, especially when things are moving fast or blending into the background.
And the other big mistake was premature completion.
Yes. Which is basically the AI version of just getting bored and deciding it's done.
Yeah.
It would just hallucinate that the quest step was finished and move on, even if the game hadn't actually registered it. Both of these errors really highlight that ongoing challenge of, grounding these big language models in the actual reality of the game world.
Okay, so it can master the game it was trained on? Pretty incredible. But the real test, the true test of a foundational model is generalization. Can Lumine take what it learned and apply it to new areas or even totally new games?
This is where the results, I think, really validate the whole approach. So first, inside Genshin Impact, they had it play the next 2 acts of the main story. Acts 2 and 3, which were completely excluded from its training data, it took 4.7 hours compared to an expert's 3.6, but it managed to generalize really complex mechanics. For instance, it figured out a puzzle with floating, moving platforms in a dungeon it had never seen before. It understood the concept of a moving platform puzzle, not just that one specific puzzle.
That's genuine understanding, not just memorization. Okay, now for the real trial by fire. The zero-shot tests on brand new games.
They threw 3 completely different games at it. The first was Wuthering Waves, another open-world ARPG, so it's very similar to Genshin. And here, Lumine was almost as efficient as a new human player. It finished the intro in 107 minutes versus a human's 101. And the errors it made were actually kind of charming. It kept getting the keys wrong, pressing E to interact instead of F, because that's the key in Genshin, and it would call the new monsters hilichurls, which is the name for the basic enemies in Genshin. It was like it was speaking its native language in a foreign country.
Huh. Okay, but what about a game that's totally different, like structurally different, a turn-based RPG?
Right. So that was Honkai. Star Rail. This is a huge domain gap. There's no real open-world exploration, no jumping, and combat is strictly turn-based. Lumen managed to finish the first chapter in about 7 hours, where humans took about 4.7. It really struggled at first. It kept trying to jump over gaps that you can't jump over. It didn't get that it had to manually select targets in combat, but the amazing thing is it finished. It even adapted its strategy by learning to lower the game's difficulty when it got stuck on a boss.
It learned to change the environment to overcome its own failures. That's incredible.
Yeah.
And finally, the ultimate visual test, right? The hyper-realistic game.
Black Myth, Wukong. This one has a much more realistic, cinematic art style, and Lumen really struggled here. It often mistook the graphics for a pre-rendered cutscene, a CG movie, and would just stop playing. It would output no-op actions, basically saying, I'm just watching a movie. It also just didn't grasp core concepts like how to heal itself. This really showed the current limits of generalization, especially when the visuals changed so dramatically.
So after all that, what's the big takeaway for you, the listener, from this whole deep dive into Lumen?
The core lesson, I think, is that the meta skills that this VLA recipe learns, specifically how to navigate in 3D and how to use 2D menus, those skills proved to be highly transferable. They worked across wildly different games, even when the art style and the mechanics were totally new. Lumen is really a proof of concept for a scalable foundation model that can learn to operate pretty much any complex PC software just by watching.
And it's just amazing that this is even possible with today's tech.
Absolutely. I mean, this was built using a pretty manageable data set, just 2,400 hours of gameplay, and on hardware that is, relatively available, 64 H100 GPUs. The next steps will obviously be to scale up the training data and, more importantly, to develop better long-term memory, something beyond its current short-term history, maybe even online learning.
But if we look beyond just making better AI gamers, what's the bigger, maybe commercial implication here of having an AI that understands game worlds on this deep a level?
Well, the integration of its perception, its reasoning, and its action allows the system to spot things a human might miss. It can find inconsistencies in game design. It can find bugs. Lumen could essentially become an automated QA tester, flagging things like confusing tutorials, broken quests, or just clunky UI design. So you have to wonder, are we heading towards a future where AI agents test our games for us during development, blurring that line between the player, the developer, and the audience, and making sure the product is polished before we ever get to play it?